Okay, hello everybody. My name is Alejandro de la Puente. I am a particle physicist, but I'm also working at the National Science Foundation. And today I'm really excited because today we have our first colloquium ever as part of a new series that we're going to host here at the Latin American Webinars in Physics. I'm very excited because I'm going to introduce a friend, a colleague. His name is Jamie Geiner. Jamie is currently at the University of Hawaii at Manoa. He's a lucky fellow. And he's currently a postdoc there. Jamie received his PhD at Stanford University, and after that he did two postdocs, one at Argonne National Lab at Northwestern University, and the other one at the University of Florida, where I had also the pleasure to see him and give a talk there. So we're excited because today we're not going to go away from physics, but we're going to stay within this physics world, but we're going to talk about aspects of computational physics, of computer science that help physicists do their jobs better, especially when we have to deal with lots and lots of data. So with that, I'm going to introduce Jamie, and the title of his talk is going to be Introduction to Machine Learning in Particle Physics. And I hope you find this really interesting. Like always, you can ask your questions through the YouTube channel on the right-hand side of the YouTube video, or through Twitter using the handle lawphysics. And with that, I'll leave you to Jamie, and thank you so much, and look forward to more of these colloquiums.
Well, thank you very much, Alejandro, for the introduction. Hopefully everybody can hear me and see my first slide, which should be up.
It's working very well.
It's working very well. Excellent. So today, I'd like to talk to you guys, give you an introduction to machine learning. And then I'll say a bit about applications of machine learning to particle physics. Not today, but soon I'll have the slides for this talk available at my GitHub page and maybe at other places as well. So my goal in this talk is first to give a self-contained introduction to machine learning for people in particle physics, astroparticle physics, and so on. And that'll be the bulk of the talk, though I'll also talk at the end about how this stuff is applied, mostly to particle physics. There's only so much time, and that's the subfield in which I work, and so that's what I wanted to focus on in terms of applications. So briefly, I'll say some words about what is machine learning, move on to a short history of machine learning, artificial intelligence, and computing, go through some of the main algorithms while introducing some of the basic ideas in machine learning, and then, as noted, talk a bit about the applications of machine learning and really focusing on particle physics. So what is machine learning? Machine learning is an approach to artificial intelligence where the algorithms learn from the data. And artificial intelligence, I think, is hard to define because what is intelligence? But I think we all kind of know what intelligence is. Of course, artificial intelligence trying to make computers that are intelligent. Machine learning algorithms come in two big classes. One is supervised algorithms. This is when the algorithms are learning from data where we know the right answer. In particle physics, this is often that we're training our algorithms on samples of events that we've simulated using Monte Carlo generators, where we'll have a sample of signal events and a sample of background events, and we use the fact that we know which are signal and which are background as part of the training. The alternative to supervised algorithms are unsupervised algorithms. And this is when we don't really know the right answer. We're not training on some data set. We're just trying to find patterns in the data. How many clusters are there? What are the clusters? That sort of thing. Now, especially coming from a physics background, when I say something like machine learning is when we learn from the data, that might seem like a trivial definition, because isn't that how we always learn, especially in the sciences? And I think the answer there is that machine learning is at least in part defined by being different than another very historically important approach to AI, which is the use of expert systems. So what are expert systems? These are the things that you build when you're doing an older approach to AI called symbolic AI, or now called good old-fashioned AI. Symbolic because it's based on knowledge that can be encapsulated in rules and equations and things like that. Good old-fashioned because this was the dominant approach in the latter part of the 20th century, but is no longer the dominant approach. And specifically, what are we doing when we build expert systems? We're figuring out how to solve problems and then telling the computer what we know, and then using the computer's ability to perform many calculations, look at many possibilities, but it's evaluating those possibilities using rules or heuristics that a human has given it. And I think the example that makes this a lot easier to understand is if we think about the concrete example of building computers that can play chess. Hopefully, most of you are at least somewhat familiar with chess. I'm not very good, but I know the rules. So if you wanted to build an expert system for chess, and of course people did this, what do? Well, you want your chess player to select what's called an opening. I mean, people have looked at the ways that you start a chess game and analyzed every set of moves that you can do. It's called the opening book. You want your expert system to pick some opening and kind of know the pros and cons in some way. You then tell your computer how to rank various moves in various positions. You tell it that, well, it's really good to have your queen. It's more important than a rook. Rooks are, in general, better than bishops or knights, and you can assign point values and so on. It's important to control the center of the board. It's good to protect your king. You probably want your rooks to have clear rows and columns to act along. You want your bishops to have diagonals that they can move along, and so on. And these are all human discovered rules that you're giving to a computer that can then use these rules to evaluate a tremendous number of positions, looking as far ahead as possible just by brute force. In fact, in the late 90s, IBM built a chess-playing supercomputer. So sort of a supercomputer, but you actually add a special chip that's optimized for evaluating chess positions. And this computer, Deep Blue, defeated the world champion at the time, Garry Kasparov, 3.5 games to 2.5 games in 1997. Deep Blue is an expert system. It was using the procedure I outlined on the preceding slide. It is evaluating 20 million positions per move, and there's basically like maybe 10-ish moves that you can make on a given turn in chess. So this is this could be 7 or 8 moves ahead. Maybe it's a little less, but 6 or 7 moves, let's say. But again, it's using a program where it knows whether a particular position for the pieces is good or not, based on the wisdom of human chess players who played a role in programming the computer. So it's an expert system. So that example was chess. But if you're thinking about sort of the great classic board games, maybe the one that leaps out at you if you have maybe solved chess is you want to think about Go. And this is a much simpler game in terms of rules. Basically, you have a board and you can put stones on the intersection of these grid lines. You have 19 by 19 points where you can put the stones, and you're trying to capture territory on the board, essentially. Even though it's a simpler game in terms of the rules, you don't have to explain castling and how all the pieces move differently and all the wonderful complexities of chess. It's still harder for a computer because you have a 19 by 19 board. So depending on how many stones are already on the board, there are 100, 200, 300 possible moves on a given turn, rather than the order 10 that we had for chess. So it's much harder for the computer to evaluate all the possible future positions than it is in chess. And so for this reason, people thought that, well, maybe we'll be able to build computers that beat humans in Go sometime in the 2020s, maybe. That's when we'll have the computing power to do this. So a group called DeepMind, it was originally its own startup. It was acquired by Google, so it's now Google DeepMind, built a program to play Go called AlphaGo. And this program is not an expert system like Deep Blue, but instead is based on machine learning. Specifically, it learned. It was trained on a data set of 100,000 games of strong amateurs, because this was the data that was available online in large quantities. And from this, it learned how to mimic sort of a competent amateur, a good but not great human player, basically just to learn roughly what someone might want to do when they're playing Go. With this background, it then trained by playing itself millions of times, so getting a huge data set. And then it's using what's called reinforcement learning, where we're rewarding it when we're rewarding strategies that win, we're penalizing strategies that lose. AlphaGo defeated the European Go champion 5-0 in 5 games in October 2015, which was the first time that a computer had beaten a human professional Go player without a handicap, without sort of basically extra points or extra moves. And this was an amazing achievement, but the center of Go is not in Europe, but in East Asia. So it was seen as important to really have AlphaGo take on one of the top human players. And so in March 2016, AlphaGo played an 18-time world champion, Lee Sedol, a Korean, in Seoul, and defeated him in 4 of those 5 matches. And this was very well followed in real time, and something like 80 million people watched the first match on TV. There's a wonderful documentary called AlphaGo about all of this that you might find interesting. Something that's fun, it's actually true of Deep Blue as well, but with both expert systems and machine learning, when you build these computer systems to solve problems, sometimes they do things that we just don't understand. And that's a fun thing, I think, to think about in general when we think about computer solutions to things that we as humans think about. So that was AlphaGo. That was the state of the art way back in 2016. But since then, the state of the art from DeepMind is a program called AlphaZero, which is something that trains entirely from self-play, and it can do games besides Go. It's actually also, basically in a few hours of training, was able to beat the state-of-the-art computer programs for shogi, which is the board I've shown on this slide. It's a sort of a Japanese chess-like game, and chess itself. So having given some examples for flavor, said a little bit about what machine learning is, what expert systems are, maybe a little bit about the contrast and competition between those approaches, I'll now go through a brief summary of the history of computing, the history of AI, and really with the idea of being a history of machine learning. But it's important to understand this in the broader context of AI and to understand AI in the broader context of the history of computers. And along the way, I'll highlight a few of the algorithms that we'll look into in more detail when we really kind of drill down on what machine learning is. So just the fun pictures I have on this slide, the one on the left, is the blueprints for one of Charles Babbage's early mechanical computers. I just love these old-timey blueprints. And then on the right, this is one of the early attempts at self-driving cars. And of course, sort of the intelligence needed to drive a car is something that now people do a lot of work into developing through machine learning. So so to start with a history of AI, I'm only going to go back to the 19th century. You can imagine going back much further. Of course, to do AI, you need something artificial that's capable of doing calculations, which broadly we should call computers. Computers or calculating machines on some level go back to antiquity, but probably the first thing that you could really call a modern computer was developed in the 1820s by Charles Babbage, who was the Lucasian professor at Cambridge. So this is the same job that Isaac Newton had, that Stephen Hawking had, Dirac had. Good gig. And it's a modern computer because it has a memory which is distinct from the processing part of the machine. It has another part of the machine for dealing with input and output, what we call I/O. Some of his later ideas use punch cards, which of course were used in computers, well into the 20th century. But these were, primitive by modern standards. His best model, and of course he made blueprints, he designed things. We know today that they would have worked, but he wasn't actually able to get them to work in his lifetime. He was a theorist. He couldn't always talk people who could actually build these things into doing it. But anyway, his best blueprint, the analytical engine, its memory was 675 bytes. You could do 7 operations per second. That's my very generic, a couple-year-old laptop. You're larger by 10 to the 9, and memory by a similar factor in speed. But still, it's a modern computer and a tremendously important step forward. An interesting note is his assistant, Ada Byron Lovelace, Byron because she was the daughter of the famous English poet Lord Byron. There are notes in her handwriting about how to actually calculate sort of numbers important in mathematics from this machine. We don't know totally the whole story if this is a collaborative effort or not, but she's really the only person who has a good claim to be the world's first computer programmer, though not in any language, just in sort of the knobs you would turn on an analytical engine. But yeah, as I noted, none of his machines were actually built during his lifetime, though people have gone back because of the great historical interest and shown that they would have worked. And in fact, there's some fun things online where they have emulators, and you can kind of run your programs on these machines, and it's fun, though maybe not so practical, but indeed these machines would have worked if they were constructed. So in a sense, machine learning also begins in the 19th century with the ideas of using things like least squares to fit curves and so on, to perform regression. And this goes back to, as maybe many things do, to Gauss in actually the very end of the 18th century, though he was maybe a little bit casual about publishing things. So this method was first published by Legendre early in the 19th century. And I'll talk about how regression and curve fitting is machine learning, because this is a very sort of familiar thing to do that turns out to contain many of the ideas that we'll ultimately want to look at in machine learning after I finish my historical introduction. So in the 20th century, of course, we get electronic computers. The early models were not amazing in terms of memory or power, but it's a huge step forward. Of course, these are these big room-sized computers with vacuum tubes and all of that. Surprisingly to me, when I learned this, I was kind of surprised at the date on this. Neural networks actually go all the way back to the 1940s. A guy named Walter Pitts, who had a actually interesting but kind of sad life, but was really just sort of an off-scale genius, just didn't do the human thing very well. A little bit later, one of the first really important algorithms, because there was nowhere near the kind of computation power to do sophisticated things with neural networks, was something you could think of as a simple neural network, but you don't have to, called the perceptron. And it was actually originally implemented not as an algorithm in software, but as a machine. And that's the sort of the room-sized thing that's the bottom of my 3 pictures on this slide. And I'll say more about neural networks and perceptrons when we're going through algorithms later. So there was already in the 40s, 50s, 60s, some of these machine learning algorithms were being developed, but basically machine learning doesn't end up being the dominant approach in AI from, say, the late 60s through the end of the century. And this is, and part of this is actually sometimes called the AI winter. It wasn't looking good for AI at all So the whole period is a machine learning winter, and the end of it is maybe an AI winter. The field was not doing well. And there's some different reasons for this. In terms of machine learning, perceptrons were probably overhyped when they first came out in the late 50s and early 60s. The New York Times in 1958 described the perceptron machine as the embryo of an electronic computer that the Navy paid for it to be built, the American Navy, I should say, expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence, which of course is very dramatic, and is not conscious of its existence. I don't think we even have today. At least I sort of hope. But we can do a lot of these other things, but certainly in 1958, this was way too optimistic. Various experts, Minsky's a famous computer scientist, pointed out some of the limitations of perceptrons in the late 60s. An important funding agency for American research, at the time Advanced Research Projects Agency, it's defense, so it's now the Defense Advanced Research Projects Agency, DARPA, became less willing to pure computational research in the late 60s and early 70s, so that slowed research in these areas. Sort of reaction to the limitations of early machine learning, when you don't actually have a lot of computing power, led to more focus on expert systems rather than on machine learning. Now, in the early 80s, there was a whole industry, private industry, building machines like I've shown in my picture on this slide called Lisp machines, which were workstations optimized for running expert system AI programs using a language that's very good for that called Lisp. But this market was disrupted by general purpose workstations and ultimately by good desktop computers from people like IBM and Apple. So that basically killed that industry, and with it a lot of the interest commercially in AI. But there were other problems too. One of them is that expert systems in general are hard to scale. I mean, it's fine to build an expert system for chess. Chess is not getting more complicated. It's still going to be an 8x8 board in 1,000 years. But with various human scale systems, you're going to want to scale things up as they develop, and it's actually hard for expert systems to learn. And the field was maybe further hamstrung by funding cuts in the 80s and 90s as well. So, but now we're in the 2000s, the 21st century, and so there's sort of two big images on this slide that I want to explain. The one sort of on the left is showing how, in a very heuristic way, how in the 80s and the 90s and before, when there wasn't as much computing power available and when the scale of systems was smaller, approaches other than machine learning, this graphic actually focuses on a particular machine learning algorithm, neural networks, were generally the best way to do things. But as we go up to higher and higher scale, which we can do with more and more computing power, a neural net's become the optimal approach. And then the second image I have on this this slide is just showing how it's an expression of what's called Moore's law, the idea that computational power increases logarithmically. But this plot actually is in a different metric. It's calculations per second per $1,000, and the increase is actually faster than logarithmic. And you can kind of see that we're reaching the point where we're going to start having, before long, it's going to be pretty easy to have machines that have computing power comparable to brains. And that is also something that drives our ability to think about doing very ambitious things in machine learning, when our computers are as powerful as the things that we already know do learning, which is animal and particularly human brains. So driven by this dramatic increase in processor power in the 2010s, we get dramatic growth in machine learning within AI. We get a dramatic growth in the interest in neural networks within machine learning. And then ultimately, we get a lot more interest within within neural networks in relatively complicated neural networks, which have, and I'll say more that will make what this is clear, that have many different hidden layers. These have become more prominent within recent years. I've shown sort of Google trends, what the big Google searches are in terms of artificial intelligence, machine learning, and deep learning. We see that early in the period, machine learning wasn't necessarily the dominant way of thinking about AI, even as late as 2004. But today, people search for machine learning more often than they do for artificial intelligence, even though machine learning is a subset of artificial intelligence. And an appreciable fraction of these queries are for deep learning. So now I'm going to switch gears a bit to talking about some of the algorithms that I've mentioned in going through the history. One that I really wanted to talk about, because I think it makes clear that machine learning is not this different, mysterious other thing that we don't know about. It's really a very straightforward extension of things that we already know about and that we already do as physicists. So I want to talk about regression. So what is regression? Well, we have some data, maybe simulated, maybe real data, where we have, which we can think of, let's think of our inputs as n vectors, which we'll call xi. Each x is a vector in, well, they're real numbers and there are m of them. So a vector in Rm. And for each of these vectors, we have some known function value, which we'll call y. So that y is given by some true function that we may never know, plus some noise term. There's always experimental error, that sort of thing. Just to introduce a terminology, in machine learning, we would call these vectors samples. The dimensions, the components of these x are called, well, the dimensions really are called features, and the vector space itself is called feature space. And there are two very important cases. One is where the yi, the true values, take on a handful of integer values, maybe just 2, 0, and 1, say, or maybe 0, 1, 2, whatever. These are corresponding to class labels. Maybe 0 means background and 1 means signal. And then we have what's called a classification problem. The other situation is where these y values can take on continuous real numbers, and then it's regression. As you can see, really, classification is just sort of a special case of regression, though you do things a little bit differently when it's classification. So how are we going to do this analysis? I want to go through this in a little bit more detail to introduce more of the big ideas of machine learning. So if you think about it, your goal in regression, or you could call it curve fitting if you want, is to find an appropriate function of our x that's also a function of some set of parameters, which here I'm calling theta. Examples of this might be maybe linear regression. So we're going to have some vector that we dot into x and add some overall constant. And here alpha and beta are parameters. And there's a choice of what kind of function we use. Is it linear? Is it quadratic? Is it exponential, logarithmic, something else? And so the choice of the model, how many terms it has, things like that are what are called hyperparameters. They're not parameters. They're sort of meta parameters. But people say hyperparameter rather than meta parameter. And to actually perform the fitting, what we're going to do is once we've chosen our function, our hyperparameters, and so on, we're going to minimize some function. It's often called an objective function. Some people call it a loss function or a loss metric, or actually a cost function is another thing it gets called, with respect to the parameters. And the classic example of an objective function, why I'm calling this least squared regression, is to have your objective function be least squares, to be the sum of the differences between what you're getting for your fit function with some set of parameters and the true values summed over your data set. And for each of these differences, you're squaring it and you're adding them up. And so and then you're trying to minimize this, of course. As we know, this can be challenging because when you look at the value of the sum of squareds as a function of your parameters, you can get local minima. So in general, you would like to be in a situation where your function is such that it's easy to calculate things like gradients, maybe more even advanced information about the function, like Hessians, second derivatives, that sort of thing. So we can use it in optimization algorithms. An important example is steepest descent minimization, but of course there are many, many others. If you're doing classification, it's only slightly different. Basically, then you're doing regression not with 0 and 1, but with what's called the log odds. You're actually trying to find the right probability for each point. And you use an objective function generally that's related to maximum likelihood ideas, and as a result ends up in an interesting way being related to entropy. So the big problem, of course, in doing anything like this is what's called overfitting. And I've shown an example of overfitting on this slide where we have some points that are little blue dots. We have the correct best fit line through these points, and they're actually generated from a function that's that line plus some relatively large noise term. And so if we try to actually fit all the points, we get maybe something like that orange curve that hits many of the points in the left plot. But of course, this is nuts. You look on the right, and you basically use the same function with a statistically equivalent data. It's just it's different noise terms and different random x values, and you don't fit the function very well at all. And this is always a problem, of course. We all know that you can fit anything if you have enough parameters, but you don't want to do that. But it's especially a problem with some of the powerful machine learning techniques I'll talk more about, like neural networks, because you have so many parameters, it's actually very easy to overfit. So we do this by, to avoid overfitting, the biggest thing you do is this sort of procedure of dividing the data set into 3 parts. The first part is what's called the training set, where you train, as the name implies, your algorithm on this training set. This is what where you actually obtain your parameters by minimizing your objective function. But then you have another set of data that you haven't fit on, where you test various choices of, say, what the function is, and you make sure that you have an overfit. And then finally, there's a third set where once you've made your decisions on what function to use, what hyperparameters to have, and found the parameters through optimization, you then see how well you're doing on yet a third set of data that you haven't used previously. And that's to give you sort of an unbiased idea of how well you fit things and if you've overfit or not. So that was what I wanted to say about regression and sort of introducing these ideas of objective functions and parameters and hyperparameters, training sets, validation sets, and test sets, and other important ideas in machine learning. So now I wanted to say some words about maybe the first machine learning to be kind of, maybe really exciting to the community, even though it was developed after neural networks. So, and this is the perceptron. And so sort of the use case for the perceptron is that we have data, for instance, shown here in this somewhat cartoonish plot, as blue and red circles. And we want to classify this data with the assumption that you can actually, that it is linearly separable, that you can draw some, well, line in 2 dimensions, hyperplane in general dimensions, that separates the data into 2 classes. So, of course, this dotted gray line, the separating hyperplane, is defined by some vector, W, and some bias, since it doesn't go through the origin, B. The correct choice of W and B will have the dot product of W and X plus B, less than 0, say, for the red points, and greater than 0 for the blue points. And then, so to actually find this W algorithmically, you take some initial guess, you evaluate W dot X plus B for each point, and if it has the right sign for a given point X, you don't do anything. But if it's wrong, you add some multiple of that data point to the vector with the idea that you're sort of pushing the vector to line up to be perpendicular to the separating plane, because it's basically in the direction of sort of the average of points that are in that class. Just a little technical aside, we can think of that bias B as just another component of the vector, and then the algorithm is the same for the bias as it is for the other weights. So this is a cool algorithm, and it works. It always converges if there's a solution, and so on. But a drawback is that it does stop, it converges, at some separating hyperplane, but there are actually many if you think about it. So here, for instance, I have slightly different data, maybe qualitatively similar, but we see that we have a hyperplane, the dotted gray line, that's very, very close to one of the data points. And of course, this is dangerous, right? We all know that there's statistical stuff in our data set. Probably the real line between red and blue is not where this line is. It's very likely that if we had a larger data set, we'd have some red point on the other side of it. So you don't actually want your hyperplane to be very close to your data points. It's much more robust to get it as far from any other point as possible. And this is so this is the same data, and we now have shown a better hyperplane separating our points. The distance from the nearest points to this plane is called the margin, and these nearest points are called support vectors. And as a result of that sort of funny name for the nearest points to the separating hyperplane, this algorithm is called support vector machines. And we find the best hyperplane in support vector machines by using Lagrange multipliers and so on to optimize the margin subject to constraints. Only these nearest points, only support vectors actually affect that margin via dot products. And that's physically reasonable. Of course, only the points closest to the boundary affect where the boundary should be. Some red point very far to the right or some blue point very far to the left has no effect on what the best way of dividing the spaces is. Now, of course, not all data is linearly separable. So you might think, well, gee, this is a real limitation of support vector machines or perceptrons in general. However, it turns out that's not the case because non-linearly separable data can be handled by some transformation of the data. An example of this is shown in the plot here. What if we just had a unit circle? We have blue points inside the circle, red points outside the circle. It's very easy to draw a boundary between the red and the blue points. It's just not a line. But if we transformed our coordinates to new coordinates that had x squared and y squared in them, well, then it would be very easy to draw a line in this new space where the data is linearly separable. It turns out you can do this in general. So as I mentioned before, the boundary turns out to depend only on the scalar product of the support vectors. And if you replace a scalar product with what's called a kernel function, you can basically find the transformation of the dot products in the new space without doing the transformation explicitly. Because you don't want to say, like, OK, in this example, it's easy. But in general, you don't want to have to think of the new space where your data actually is linearly separable. You want to pick some kind of kernel function that gives you the right answer. And if you have a sufficiently complicated kernel function, it'll be successful for many different possible transformations. The example here is just if your kernel was, instead of the dot product between two vectors, the square of the dot product. If you wrote that out component by component, you would see that it actually is a dot product in the transform space I showed above. And you can also convince yourself if the kernel were some long polynomial, it would work for arbitrary, you could do a boundary that was an arbitrary polynomial function, for instance. And an exponential would get you, of course, a long way. So really, this kernel trick lets you use support vector machines very generally, which is an incredibly powerful result. But unfortunately, when you start using these nonlinear kernels, actually doing these calculations gets to be very computationally intensive, which is part of why SVMs probably had their heyday in the early 2000s, but now are less popular than, say, neural networks, which is my next example. So I'm going to explain how a neural network works. I'm going to basically work my way through this diagram of a particular neural network. Though first, I wanted to go back to what I was saying about regression, where you'll remember that our goal was to find some function f with parameters theta, and it's a function of x, which is some vector in our input space. And then that we're finding the best values of theta by minimizing some objective function. Well, that's all still true for neural networks. So this is actually very familiar. The only thing that's changing is that instead of our fit function being some kind of linear quadratic function that we may be more familiar with, or a Gaussian, say, our function is this neural network with some particular architecture. The architecture is specified by hyperparameters. The parameters that we're obtaining by optimizing some loss function, which might be something like least squared still, are the weights of the neural network, which we'll see what those are in a slide or two. And it's the same workflows for other classification regression problems, the same issue of taking our data, having a training set, having a validation set, and having a testing set. It's just that now we have a more complicated function. And so what is this function? Well, this function involves different layers. The first layer is what's called the input layer. And we have one of these input neurons. The circle things are neurons. And neurons are little machines that do something very simple. So here our neurons look for a component of our input vector, and that's their output. So the x1 neuron tells us what the x1 component is of our input vector x. The x2 neuron, it's the x2 component, and so on. We also have a bias neuron so that we can have some kind of offset. It's not true that the vector x would map to 0. The next step involves both weights and a hidden layer of neurons. So these weights we can describe as wij. We're describing, the I and j are telling us which neurons in the input layer are connected to. Ij is describing a weight that connects some neuron in the input layer j to some neuron in the hidden layer I. And I think you can kind of maybe stare at this for a second and see that this means that the inputs to the neurons in the hidden layer are given by matrix multiplication. So we look at a particular hidden layer neuron, say H1, and its input is W10 times the bias neuron output 1 plus W11 times the output of neuron 1, which is X1, and so on. Since this is really just matrix multiplication, matrices, you could say tensors. This is why, for instance, one of the most popular frameworks for working with neural networks is called TensorFlow. Google, to try to speed up neural network calculations, has developed what are called tensor processing units, which are dedicated computers for doing these sorts of manipulations, that sort of thing. So now that we have inputs to the neurons in the hidden layer, each neuron takes its input and applies some function y to this input. And it's important for that function to be easy to evaluate computationally, to have relatively compact output, to be differentiable, and we'll see why that's a big one, and to be monotonic. And so normally this is something like a sigmoid function or the hyperbolic tangent. And this function y is called the activation function, or activation of the neuron. Now in this network, we have another set of weights, which multiply the outputs of the hidden layer neurons to give us the input to one output neuron. And then we can apply an activation function to the output of this output neuron. And that gives us the final value of our function, f, which is a function of parameters, really the weights, w and x. Since we chose our activation functions to be analytically differentiable, and since the input to a given neuron is found from the previous layer by matrix multiplication, it's actually relatively straightforward to calculate the gradient of our objective function, something like sum of squares or something like that, with respect to our weights using the chain rule. It's just composition of functions. And doing that in sort of a specific efficient way is called backpropagation. That's a word you'll see a lot. And there's also other information that we can obtain, things like second derivatives, Hessians, that sort of thing. And so using, function information, gradient information, maybe Hessian information, we then use some optimization algorithm to minimize the objective function or the cost function with respect to the weights of the neural net. And that's what it means to train our neural net. Generally, there are many local minima in sort of the space of weight. So this may be a non-trivial problem, and people think a lot about the best way to do it. So in our example, we had a single hidden layer of neurons, and data moves only in one direction, from the input towards the output. So having a single hidden layer means it's what's called a shallow neural network. Having multiple of these hidden layers, which you could easily see what the extension would be, these are called deep neural networks, and using them is called deep learning. And of course, that's a very important term nowadays. The fact that data moves only in one direction, that means it's called a feed-forward neural network. The alternative, where we could take some value from a given layer and move it back to a previous layer, leads to what are called recursive neural networks. And that's a very interesting area of study. So I'm just kind of saying this because it explains a lot of terminology that you'll see. I don't always think it's the most helpful way to think about things. But we could think about what we do in the perceptron algorithm, where we evaluate the dot product of a weight vector with an input vector. Well, this is actually, if you think about it, this is a neural network with weights as it was before. There's our same input layer, but the weights are only mapping to a single output weight, where the activation function is basically just checking whether the sign of w dot x plus b is the same as the sign of the label of that point. So you could think of a perceptron as an extremely shallow neural network. It's even shallower than a shallow network, and there's no hidden layer. But you do see this terminology where especially other neural networks are referred to as multi-layer perceptrons. I don't know if that's useful, but I wanted to explain this connection in case this is something you encounter when you're looking at the literature. So my fourth example that I'll go through relatively quickly, what are called boosted decision trees. I'm talking about this because this is an important method. Anymore, I'd say more in particle physics than probably the broader machine learning community, though it is an important algorithm. So boosted decision trees obviously involve decision trees. And this is a series of yes or no questions that identify bins of data, which given signal purity, if we're thinking about signal versus background. So I have an example here where we have three signal points for which the first variable is 0, the second variable is 1 for the first point, and so on, and three background points. Sort of the best question we can ask is, what's the value of the first of these variables? And if we do a cut at 1.5, if we satisfy this cut, there's a bin with 4 events, 3 signal and 1 background. And if the answer is no, we get a bin with 2 background events. Now, there's no need to subdivide the no bin. It's already pure background. But we can then apply a cut on the other variable, the other feature, to divide the yes bin into a bin with 3 signal events and a bin with 1 background event. So in this example, we showed that decision tree is a very good classifier for our sample data because we've correctly classified every point in our training set, at least. And you can always do this for a sufficiently long tree. You can just have enough yes/no questions that you separate every point, unless, of course, there are 2 points with the same inputs in a different label, and then you can't. Now, you can't do this for a short tree. You need some number of branches to actually do this. The problem is if you're doing a really long tree to fit your training data really well, you're probably overfitting. You're probably getting some of those yes/no questions you've chosen based on data that's noise. You don't want to do that. So you want to use short trees. Those are much more robust with respect to noise, statistical variance in the training set, and so on. So you really want to have what's called a weak classifier, a short tree. But in that situation, the bins at the base of the tree will not be pure signal or pure background in general. So there's a procedure for building strong classifiers out of weak classifiers called boosting, which involves things like reweighting the events which are misclassified and rerunning the algorithm and so on. And the resulting algorithm, this is called boosted decision trees, and it's a very important algorithm in particle physics. Which brings me to my final section, which is machine learning and particle physics. So of course, machine learning is an important part of data analysis and experimental particle physics and elsewhere, but I'm focusing again on particle physics. I would say really for two major use cases. The first is identifying physics objects. Is a jet a B-jet, that sort of thing. The other, of course, is determining what the underlying process is for some event. Is it signal versus background? Of course, we always do curve fitting. We almost don't talk about this machine learning, though it's an important point that it is actually machine learning. But I would say the main algorithms are things like neural networks, mostly shallow at this point, but there's a move towards deep learning, boosted decision trees, and things like likelihoods derived from the data. Historically, actually, a lot of the discussion in particle physics has not been of machine learning versus expert systems, but of multivariate analyses versus single variable analyses. And so I've drawn this sort of Venn diagram here to illustrate, when is something machine learning, when is it multivariate, when is it neither. And basically, the idea is that most machine learning algorithms are algorithms that use multiple variables. So technically, you can have machine learning for a single variable. And most multivariate analyses, most analyses that use many different variables for doing data analysis are machine learning techniques, though some of them aren't. And of course, the main toolkit in a very popular framework for doing experimental analyses called ROOT is called TMVA because, again, the emphasis historically was on multivariate analyses versus single variable analyses, not so much on machine learning per se. Now, of course, it's clear why we'd want to use a multivariate analysis. You want to use more information if you have it. But as I've said, multivariate analyses aren't necessarily machine learning algorithms. Two examples of important multivariate analyses that are not machine learning algorithms are what's called the matrix element method, which is something I've worked on a great deal in my own research, which is an approach where we're determining the likelihood for signal and background directly from theoretical information, from the differential cross sections. Another approach is something we're all familiar with, is if you do a analysis where you have cuts on many different variables and you didn't find your cuts by looking at your data, but just by sort of what's physically reasonable. That's also actually a multivariate analysis that's not machine learning. So why is machine learning important here? Well, there are a lot of things in particle physics that are hard to model sort of analytically, and you really kind of do want to look at simulated events. And that's because of things like hadronization, showering, and especially detector response are a lot easier to understand by a Monte Carlo simulation using tools like Pythia and Herwig for hadronization showering, things like Géant to model detectors, to generate realistic events. And then machine learning can tell you about how to classify, say, signal and background events once you know what realistic events look like. And in practice, some machine learning is almost always necessary for this reason. I'm running a little bit low on time, so I don't necessarily want to dive too far into this. But I'll say that, excitingly, the matrix element method was part of the discovery of the Higgs on CMS. But even there, even though the matrix element method is not a machine learning technique, what they actually used in their analysis was a 2D likelihood found from the data, so using machine learning, where one variable was a matrix element method variable, and the other variable was the invariant mass of the 4 leptons, which was smeared somewhat because of detector resolution. So historically, a lot of the neural networks used in analyses are shallow networks, one hidden layer. But people are transitioning to deep learning because they're a little bit better. And this is a plot from a paper of I guess a few years ago now, that showed that for a particular analysis for Higgs to tau tau, you could gain almost a sigma, half a sigma to a sigma, depending on exactly what you're comparing, using deep networks rather than shallow networks. So broadly, why are people in physics and particle physics especially interested in the same things that we're interested in the tech sector, well, basically, in both particle physics and in Silicon Valley, you deal with a ton of data. The LHC produces, tens of petabytes a year. I mean, terabytes, you could have in a hard drive. Petabyte is, 1,000 times bigger than that. But at Google, say, they were producing, 10 to 15 exabytes, so another factor of 10 to the 3, already in 2010. So it's got to be a huge number today. People have talked about the future, especially with things like the Internet of Things. You're talking about tens or even hundreds of zettabytes, so even another factor of 3 beyond that. So a tremendous amount of data. You want to use your data in a smart way. Generally, that means machine learning. However, one challenge is that the goals are sometimes different between physics and the tech sector. And a lot of that is because, in physics, we're very concerned with establishing sort of true statements about the world with a high degree of confidence. We don't call something a discovery unless it's 5 sigma, which is a tremendously low p-value. So you're really interested in knowing, about very extreme, very strange background events, whereas, a private company isn't so interested in what 1 in a million of their customers do. I guess unless they're very rich customers, they're more interested in what the typical user does. So there's some difference in focus. In both sectors, I think it's important to understand why analyses work. Though because we in physics need to understand these tails of distributions, it's probably even more important for us. So to wrap up, I would say that machine learning in its broadest sense has always been part of experimental particle physics. There are many algorithms for doing machine learning, since it's a very broad idea of learning from the data. There's been a great excitement in recent years from deep neural networks, from deep learning, which will play a larger and larger role in particle physics and elsewhere. I think in particle physics, ultimately displacing shallow neural networks and boosted decision trees. But this is a very fast developing area, so stay tuned, and thank you.
Thank you, Jamie. Thank you so much. Let me turn this to me and my camera. Well, thank you for the talk. It was really interesting. I have lots of questions, but before before I ask my questions, I'd like to open the floor for questions, and then also look at some of the questions that were asked by anyone during the transmission. So, does anyone here have a question I would like to ask? Oh, hold on. I'm still presenting to everyone. Sorry. Now I stopped it. Okay. All right. Sorry. There's some things that have changed with Google Hangouts. Well, let me just ask the first question really quick. So a lot of people say AI and we're gonna make a lot of progress, but it seems like we still need lots and lots of data for things to learn, right? And in particle physics, we still depend a lot on the models we use and the simulated part of the data in order for things to learn. Is there a way we're ever going to be able to just use how we observed events to make decisions as to what events we're observing, and then sort of translate that to a model? It could be like a phenomenological model, but in that sense, we're losing the dependence on the standard model and how we differentiate signal and background, rather than working with what the machine learns and then try to construct a phenomenological model that could lead to new physics, and then develop a model from that. I don't know.
I think the basic answer is that it's hard, right? Sort of the more straightforward thing to do is supervised learning, where we're training on data where we know the answer. But of course, we're very sensitive, as you point out, to how we have simulated the data. So ultimately, what you would want to do, the sort of things you're talking about, would be to have very powerful unsupervised learning procedures that could just maybe look at the data and know sort of what to do with it. But that's hard. That would probably involve having more powerful sort of general purpose AI, something that people talk about. I mean, ideally, you could imagine if you had a sufficiently powerful computer, it could do everything we do. Our brains are just computers, so it could do it. It could even be more powerful, and then it could do anything we do at all. But that's not right around the corner. That's some years in the future. I'll note briefly that for addressing the specific challenge of, oh, gee, are we learning from, some feature of our simulation rather than something that's really there in the data. There are techniques like adversarial learning, where basically you have an automated way of seeing what's fooling your neural network, and then you can improve based on that iteratively. That can help you understand if this is, oh, gee, maybe Pythia gets something a little wrong, or whether it's something else.
Yeah, because you could imagine just out of just talking about LHC physics for now, you could imagine just having a machine learn, supervised or not, through just calorimeter information, right? And then
absolutely.
Just be really,
something that I think is exciting is we think about doing this on, we think often about algorithms on sort of physics objects, but of course physics objects themselves were constructed maybe even through machine learning algorithms from underlying data. And in principle, in the future, we can just go straight from the underlying data. Actually, if you look, this is maybe a bit of an aside, but I think an interesting one. If you look at very future colliders and extrapolate developments in electronics and in computing power, you could really kind of read in everything and not have a trigger, and just and it could all be processed in some sort of very intelligent way. And that's the future.
And then the last thing I have to ask is, when you talked about the Go program, it learned from amateur data online, and then it was able to beat a professional, like a completely, like the best person at Go.
Well, there were two steps, and the first step was learning from amateur players online, and that's just because when you can make, 300 moves, you want to at least start by, you want to keep things reasonable for starters. The big thing was that the program played itself millions of times, and that's where it went from being, maybe a competent amateur, which I'm not. I don't really even play Go, but from maybe someone like me at chess to a world champion if it were chess, kind of. It's from playing itself and learning from its mistakes and trying every different thing. And
that's what I was. Okay. So that's important, right? If you just give it a set of rules, and then just let the machine optimize its own playing, and it can get better by itself. And whether or not it gets better than the best person, that's
right.
It still got better, right?
Right. That's just a threshold. Though it is interesting that now even that version was better than the best person. And actually the more recent one, Alpha 0, is totally from the self play. It knows the rules, and then it goes through
That's amazing.
Just plays and plays and plays, and in a few hours it can beat anybody in chess.
That's amazing. Anyway, thank you for answering my questions. Does anyone here have a question or two or three or four?
I have a question here. Well, first, thank you very much for this very nice talk. And my question is, well, according to what your conclusions are that the community in particle physics have been using machine learning for the beginning. And then basically what they're doing is changing the techniques. And now they're changing to deep learning, let's say.
Right.
But the problem that I see is that, at least in deep learning, or also in these other machine learning methods, we physicists always want to have control on what is happening.
Right.
And in deep learning, it is not happening. But I don't know what is your feeling about the community now changing to deep learning, in which we are not completely sure what is happening in the machinery.
No, it's an incredibly important question, right? I mean, when you use more sophisticated algorithms, when you use neural networks, when you use deep neural networks, you have a lot of power to, in principle, learn from information in your data. But it's at the cost of having learning things that a human can't see, and hence maybe we don't really understand. And there's a lot of fear, especially in physics, that maybe we've learned from a systematic. And this is not a real difference. And that is a problem. So if these become, as I think it probably will, as this becomes more and more important, there's going to need to be more and more research in learning how to understand what we're learning from the data. But yeah, it's a huge issue.
Is anyone else? We're looking at.
Yeah, I have a question for Jamie. So, well, also it was very nice the talk that you gave. Like a lot, especially because you you teach us about all the keywords important in
sure.
machine learning, because for
Buzzwords.
someone that is not doing machine learning, the only phrase that is machine learning itself, but not the important part. So in the case of particle physics, in experimental particle physics, how long is usually a program can run to have some results, in the sense, because other methods that are more expert tends to be more efficient in regarding the computational power, but they lack the feature to learn from or to extract these hidden physical meaning that are in the data. But more or less.
That's a good question, and I don't really know quantitatively. I'm a theorist rather than an experimentalist. I would certainly say that I think why there hasn't been more deep learning at this point is really in part the time issue, but not the time to run, to train once with a deep neural net, but because, and this goes back to the last question, because there's so much concern about understanding systematics and so on, that you're not just going to, do a given analysis once. You're going to do it many, 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 many times on different parts of your data, varying parameters, maybe modifying different variables to see how they're having an effect on your data. So having that sort of deep understanding of where your sensitivity is coming from, if you're also going to pay some 10 to 20 whatever feature penalty in terms of how long it takes you to run each step, that's very painful. I mean, as you know, analyses already take a lot of work and a lot of time. So of course, the nice thing is that computers get better and better. So so that's not going to be a roadblock looking forward, though I think it's still a consideration right now.
Yeah, just another question that is also a kind of curiosity also for the people that is watching the YouTube stream. So in your case, or for more PhD students or physicists, all these tools of machine learning, how you learned about this? Because let's say that it's not like a common course that now, maybe now that people following courses of that, but for our generation, let's say, this is something that is completely new. So.
Yeah, I think right now, unfortunately, it's not as easy as it should be. So I know personally, for me, it's a combination of actually just going to the course at the university where I am now, the University of Hawaii, of online courses, and then trying to read about things. There's some great online textbooks, but they're generally a little bit more heavy duty on the statistical side than you might want just to be able to apply things. I'm thinking in particular the Elements of Statistical Learning, which is one of the major texts in which you can just Google for and download, but it's it's from people who are really ultimately kind of statisticians who are interested in being somewhat of mathematicians about this. So I think there's really still kind of a gap really in terms of is there one simple reference to give to say beginning experimental graduate students so that they can really understand these methods, and I think a lot of it's passed down person to person and so on. So yeah, I don't have a great answer for that, unfortunately, other than personally for me it's been from a variety of sources.
Yeah, like most of us are we learn by experience
Yeah.
By doing the stuff, we learn to use the tools that we know. Thank you.
Another question that it's interesting. There's another one of those emerging technologies, but based on a lot of years of theoretical work, quantum computing.
Yes.
Do you think the algorithms, or as the things we're trying to address get harder, we're gonna need algorithms that use at least a portion of them be quantum mechanical algorithms, quantum algorithms?
Yeah, well, that is a really great question. That's very much an open question. People are starting to look at the research level. This is the cutting edge into quantum computing for machine learning. Not a lot of people, because this is really the very edge, or maybe a little beyond the edge. There are reasons to be hopeful that it would be helpful. In particular with in principle with quantum computing, because you're looking at many states in superposition. you might be less likely to end up in your optimization algorithm in some being dominated by some local minimum. Hopefully you're going to be somehow sensitive to the global minimum. Of course, because it's quantum computing, you're doing all these states in that are in superposition, but you're actually you get one answer and somewhat probabilistic. And it's not obvious to me that you always are going to be able to optimize as well as you'd like to. Maybe these local minima are dominant. Maybe there are many more of them or something like that. But it's absolutely an exciting research level question whether quantum computing is going to be a big part of the machine learning story ultimately.
Well, I have a question here.
Yep.
My question is regarding it's not a secret that the big player in this machine learning thing is industry rather than academy. And are you aware of some contacts between industry, I don't know, Google or Amazon, the big players in this, with academia?
Right. Well, there's two levels of that, because when we say academia, we can mean kind of two things. We can mean any academia, including computer science academia, or we can mean physics academia. And actually, in sort of the research arms of big tech companies are a lot of people who are actually still in academia and computer science departments. You know, the big, Jan LeCun is a huge guy in this area who's at Facebook, but he's also at NYU. Jeff Hinton. There are other big people in machine learning who have both academic affiliations and affiliations at major tech companies in their research groups. So at that level, there's a lot of interaction. I mean, there are important questions about, for instance, do too many people who get PhDs in machine learning end up in tech versus in academia? Is there some concerns about who's going to teach the next generation? And then, of course, I think people do. I've had conversations with people at Google Brain and places like that who, certainly people are interested in solving problems of academic science, of physics or of chemistry or medicine's a big one, of course. Now, is it the right amount? I don't know. I don't think I have a really developed opinion on that yet.
But what I hear a lot is so using this to address highly complex human challenges, right? And when physicists know how to do this, when other scientists know how to do this, they definitely contribute to social problems, like people talking about IoT, right? How is that going to help us transition into the next generation of cities and communities or whatever? Sure. So I think I see it more as an opportunity for people in the physics community that know how to do this to either transition out of academia if they want to, or just be part of something else if they want to as well. I think of this as a skill that we are that we could have if we wanted to, if we work on things like this. So,
and I'll make just a point, since I know you have a lot of interest around education. I think it's important that we make sure going forward that our undergraduates and graduate students are good enough at this that it's a relatively easy transition into the private sector.
Oh, definitely. I think
emphasis we have now. Yeah.
I think definitely your colloquium does this, right? We're trying to motivate people that learning this could contribute to your science, but also to other things if you want. So, but I agree, we should definitely be addressing this in the curriculum somehow. I don't know how yet, but
yeah, it's a hard question because you can't cut electromagnetism to have them learn more computer stuff, but it is a useful skill.
But we could definitely take some of this on the curriculum and see if we can implement certain examples that use machine learning, or at least the primitive aspects of machine learning, which then transition into the more advanced machine learning. Anyway, does anybody else would like to ask anything? This is going to be available in GitHub, right? Your talk, and then
within the next day or so. I realize there are a few little typos I'll fix. But
take your time. Take your time, and we will share that. And thanks for being our first.
Thank you very much.
I really appreciate it.
I have a question over here.
Sorry, Joe. Go ahead.
So you mentioned at some point the overfitting, right? And,
Right.
and you showed it with some very extreme examples. But I was wondering if there's a procedure to figure out if you are really overfitting or not, right? Because of course in your example it was obvious, right? But I can imagine more subtle situations.
Sure. No, it's tricky. It's tricky, and that's why you have the, you have the test set where you see how well you do with your fit on some data that you haven't used yet. There are also more maybe more algorithmic ways of trying to avoid overfitting. The big one is called regularization, where basically instead of optimizing your objective function, you optimize your objective function with an additional term that penalizes you for using a very complicated function. So the example might be you have some vector of weights. Now, in addition to optimizing your function, you minimize, say, your function plus some number times the length of your weight vector. And that the idea there is that you're encouraging you to have as few parameters in your function as possible. I think answering that question in a great deal of generality, beyond just sort of looking at your test set and making sure that you still fit well with whatever function you have, is a real challenge. And actually, especially when you look outside of physics to other areas of interest, there's a tremendous amount of overfitting, right? I mean, if you watch sports like I do, you'll hear someone say, well, this team has never come back when down by more than 2 goals in the second half on Tuesdays. It doesn't mean anything. It's overfitting, but that's what people do. I mean, so it's a really big challenge and a really big question, and I think it's just it takes vigilance and common sense, and maybe it's hard to quantify those things.
Okay, I see. Thank you very much, and thanks for the colloquium. It was fantastic.
Oh, thank you.
Yeah, with that, I like to thank our speaker. I'd like to thank everyone for being here, and I look forward to our second one. But stay in touch, because we have our 7th season just begun, and we look forward to a lot more talks about physics and a lot more talks about general aspects of science that we physicists are doing and that we could do anywhere else. So thank you very much, and have a great day, guys.